Welcome to today's Explainer, everyone. I am absolutely thrilled to be guiding you through a truly fascinating journey today. We're going to follow the path of an object traveling through Earth's gravity, starting right down here on the ground and venturing all the way out into the deep mysteries of space. Here is our quick roadmap for today's lesson. We'll start with variations in gravity, then look at mass versus weight. Next up is understanding free fall, followed by energy and escape velocity, and we'll wrap up the entire journey with space and gravitational waves. All right, let's jump right into Section 1, Variations in Gravity, Journey from the Center to the Sky. Now, a lot of us naturally assume that acceleration due to gravity, what we call small g, is a strict, universal constant everywhere on the planet. But actually, as you'll see, that's not true at all. To put this into perspective, the data is incredibly interesting. On the Earth's surface, g is an average of 9.8 meters per second squared. If you climb all the way to the peak of Mount Everest, 8.8 kilometers up, it barely changes. It's still roughly 9.8. But go higher to a weather satellite at 400 kilometers, and it drops to 8.7. And if we look at a communication satellite orbiting at a massive 35,700 kilometers, well, g dramatically plummets to just 0.225. Gravity slowly but surely weakens as we move further away from the Earth. So let me ask you this. If g decreases as we go up into the sky, what happens as we go deep inside the Earth? Does it increase or decrease? You might intuitively think, hey, it must increase because I'm getting closer to the center. But actually, it decreases. This happens because as you dig deeper, the actual portion of the Earth's mass that is pulling you towards the center gets smaller and smaller. In fact, at the exact center of the Earth, the value of g becomes absolutely zero. And this brings us to other planetary bodies. You see, every planet has a totally different mass and radius. Take the moon, for instance. The value of g there is roughly 1/6 of what it is here on Earth. That means if you use the exact same muscle force, you could jump 6 times higher on the moon compared to the Earth. Imagine how fun that would be. That perfectly sets up Section 2, Mass versus Weight, Clearing the Confusion. To really understand how gravity affects objects, we need to get our definitions straight, because in daily life, we mix these two words up all the time. Here is the absolutely crucial distinction. Mass is a scalar quantity. That means it's simply the amount of matter present inside an object. It's measured in kilograms, and it is completely constant everywhere in the universe. Weight, however, is a vector quantity. It is the actual physical force with which the Earth attracts that matter. Because weight is a force, we measure it in newtons, and it totally changes depending on your location and the local value of g. Let's connect this to real life. When your friend Rajiv steps on a scale at the gym and says he weighs 75 kilograms, scientifically speaking, he is actually talking about his mass, not his weight. His true scientific weight on Earth, the force gravity is exerting on him, is his mass times g. That's 75 multiplied by 9.8, which gives us 735 newtons. So those weighing machines in shops, they're essentially just comparing two masses, even though we colloquially call it weight. Right, let's shift gears to Section 3, Understanding Free Fall, Dropping the Object. What exactly happens when we hold something up high and just let it go? By strict definition, free fall is when an object moves exclusively under the influence of gravity and nothing else. Now on Earth, if you drop a stone, it falls, sure, but it also experiences air friction and a tiny bit of buoyant force. Because of that, perfectly true freefall is technically only possible in a complete vacuum, where absolutely no other forces are acting on the object. Don't let the math worry you. We use Newton's general equations of motion here, but they simplify beautifully for freefall. Since you are just dropping the object, your initial velocity, or u, is literally zero. And your acceleration, a, is simply replaced by the acceleration due to gravity, g. Because of this, the math gets so much easier. Velocity v becomes g times t. Distance s is half gt squared, and so on. But wait, what if we throw the object upwards instead? In that scenario, our mathematical acceleration becomes negative g. Why? Well, because gravity is always pulling downwards. It is directly fighting the upward velocity of your object. That negative sign is just the math's way of showing the physical reality. The object is slowing down as it fights against the Earth's pull until it finally stops and falls back down. This actually brings up a brilliant historical anecdote. Galileo supposedly dropped two spheres of totally different masses right off the Leaning Tower of Pisa. He did this to prove a very specific point. The value of g does not care about mass. Irrespective of how heavy they are, objects falling freely from the exact same height will hit the Earth at the exact same time. Okay, but what if we throw an object upwards so incredibly fast that it never comes back down? Welcome to Section 4, Energy and Escape Velocity, Breaking Free. To grasp this, we first have to look at gravitational potential energy. The formula is negative g times m divided by r plus h. Now, you might be wondering why the negative sign. Well, if you are at an infinite distance away from Earth, the gravitational force is basically zero, right? So potential energy is assumed to be zero. Since energy increases as you go higher, for distances closer to Earth, the energy has to be less than zero. Hence, it's always a negative value. And that leads us straight to escape velocity. This is the precise initial upward speed an object needs to completely overcome Earth's downward pull and vanish into space forever, without ever falling back. To pull this off, the object's total energy must be perfectly balanced, so it has enough kinetic energy to reach that infinite distance. Let's walk through the logic using the law of conservation of energy. Step 1, we calculate the total energy at the Earth's surface. That's kinetic plus potential. Step 2, we find the total energy at infinity. Since it comes to rest there, kinetic is zero and potential is zero, meaning total energy is zero. Step 3, by setting the total surface energy to equal zero, we mathematically solve for V escape. When you actually plug the mass and radius of the Earth into that derived formula, you get a staggeringly huge number, 11.2 kilometers per second. That is Earth's escape velocity. Any spacecraft we launch to the Moon or Mars has to exceed this massive speed initially, just to rip itself away from our planet's gravitational grip. Finally, let's step away from classical mechanics and venture into Section 5, Space and Gravitational Waves, the Modern Frontier. You know how dropping a stone into a pond creates ripples? Well, massive astronomical objects do something very similar. They emit gravitational waves. These are literal ripples on the very fabric of space-time itself. Albert Einstein theoretically predicted their existence back in 1916. But because these waves are unbelievably weak, it took exactly 100 years of technological progress before the highly sensitive LIGO Observatory finally detected them in 2016. A massive triumph for science. Speaking of space, I want to pose a very common misconception to you all. Why do astronauts float around in a spacecraft? Is it because there is zero gravity out there in space? Take a moment and think back to the data we looked at right at the start of our lesson. Here is the absolute truth of the matter. Gravity is definitely still there. A space station typically orbits just a few hundred kilometers above the Earth. As we saw earlier, at that height, the value of g is only about 11% less than it is down here on the surface. That is plenty of gravity. So the height of the spacecraft is absolutely not the reason for their weightlessness. The real reason they float? It's our old friend freefall. The spacecraft, the astronauts, everything inside, they're all traveling at a tremendous horizontal velocity along their orbit. The Earth's gravity is pulling them down, but because they are moving forward so incredibly fast, they continuously fall around the curvature of the Earth. They are in a constant, never-ending state of freefall together, making everything appear weightless relative to each other. Well, we have definitely covered a lot of ground today, from the changing values of g to the elegant math of freefall, breaking free with escape velocity, and the reality behind floating astronauts. So I will leave you with this final, provocative thought for today's explainer. If gravity has the sheer power to shape absolutely everything, from a simple stone dropping from your hand to invisible waves rippling across the fabric of space-time, what else out there in the universe is falling right now that we simply cannot see? Keep questioning, keep calculating, and I'll see you in the next explainer.